Hello and welcome to the second session on acids and bases in chemistry. In this session, we'll be talking about weak acids and bases. In the previous session, we introduced such things as pH, KWs, KAs, the acid dissociation constants. We also introduced the concepts of strong and weak acids and bases. We introduced the basic sort of definitions to do with the Arrhenius and Bronsted-Lowry definitions. And we talked about how acids and bases could exist in different solvents other than water, including things like ammonia and ethanol. So with regards to this session, we're going to be talking, of course, about weak acids, which make up the majority of acids in our everyday existences as chemists, as human beings. So we're going to be talking about solving problems involving weak acid equilibria. So the weak acids are typified by the fact that they don't totally dissociate. So we'll be taking a problem-solving approach for this. And the first step is, as always, to write a balanced equation. We might not always be given a balanced equation, and thus it is important for us to make sure that we are writing a balanced equation. Then we'll write out our expression for Ka. So remember that Ka is just a special form of Kc, the equilibrium constant, which we saw in previous lectures. And then we'll be asked to define X as the change in concentration that occurs during the reaction. So X is this idea that in our dissociation reaction or in our weak acid equilibria, there will be a certain fraction of our total acid that is dissolved in the water, for example, in the solvent, which will dissociate, and we will term that X. Then we will construct a reaction table in terms of X, and we will make assumptions that simplify the calculation. So we will then substitute values into the Ka expression and solve for X. So the assumptions that we usually make are things like, since typically the Ka values are very small, the amount of the original concentration which dissociates is usually very, very small. And so we can usually assume that for all intents and purposes, the original concentration is going to, of the acid is going to be the same as after it has dissociated. So for example, say we mixed 0.4 molar acetic acid in water, we would end up with 0.4 molar at the end. It should be reduced by a certain value X, where X is the amount that is dissociated into acetate and the hydronium ion. But since it's a very small amount that actually does dissociate, we'll just use it as 0.4 molar at the final equilibrium concentration. And we can only make that assumption if there's less than 5% of our total acid has dissociated. And we'll see how we can do calculations like that to check later on. Then, of course, we need to check that our assumptions are justified. And one of the assumptions there is that less than 5% of our acid has to be dissociated in order for us to get a justifiable value. So a few housekeeping notes. So the notation system, so molar concentrations are always indicated by square brackets. So if you see, for example, HCl inside of square brackets, that's the constant, that is read as the concentration of HCl. A bracketed formula with no subscript indicates an equilibrium concentration. So the assumptions that we typically make is that water from the autoionization, hydronium and hydroxide from the autoionization of water is usually negligible. And so a weak acid has a small Ka and its dissociation is negligible. Therefore, the concentration of HA is going to be approximately equal to the initial concentration of HA. That's what I was talking about before whenever I said if we dissolved 0.4 molar acetic acid in water, we'd probably still have effectively 0.4 molar acetic acid undissolved in our solution. So here is an example of how to find Ka of a weak acid from the solution pH. So phenylacetic acid, the formula is given there, can be simplified as HPAC. So this builds up in blood of persons with phenylketonuria, an inherited disorder that, if untreated, causes mental difficulties and death. So a study of the acid shows that the pH of 0.12 molar HPAC is 2.62. And so we're asked, what is the Ka of phenylacetic acid? So of course, as always, our first step is to create that plan of action. So we're going to want to start with a balanced dissociation equation and write the expression for Ka. Then we assume that the hydronium concentration from water is negligible, and we use the given pH to find the hydronium concentration, which is going to be from our HPAC. So since each HPAC that dissociates produces one hydronium and one PAC minus, then we're going to have equal concentrations of hydronium and phenyl acetate anions, and then we're going to also have then the concentration of the dissociated phenylacetic acid. So we assume that the dissociated equilibrium concentration of phenylacetic acid is going to be approximately equal to the initial concentration of phenylacetic acid, because phenylacetic acid is a weak acid. So what does this sort of have, and what does it mean for our measurements going forward? So we first of all form our Ka, which is our acid dissociation constant. Remember that in Ka, we don't explicitly write out the water concentration because it's included in this Ka term, because Ka is, if we recall from the last session, Kc times the hydronium concentration, or the water concentration, sorry. So that's going to be products over reactants as usual for our equilibrium constants. This is just the acid equilibrium constant. We can, since we know the pH, we can find the hydronium ion concentration by rearranging the pH equation, where pH is equal to minus log to the base 10 hydronium concentration. So here we're going to write out our reaction table that we saw back in module 2 for our equilibrium. So check out those lectures if you want to know more about these sorts of tables. So we're going to be talking about our initial concentrations, where we said that we had 0.12 molar phenylacetic acid that was dissolved in water. And so initially we're not going to have any hydronium or any phenyl acetate, because these have not been produced yet, because at the point of dissolving, it's still all in this phenylacetic acid form. So then the change is going to be minus X, where X is the amount of dissociated acid species which are produced. And so since we have some hydronium and some phenyl acetate produced, that must mean that we have some phenylacetic acid. The concentration must be reduced. So our equilibrium concentrations then are going to be 0.12 minus X, where X is, of course, that dissociated fraction. And then X is going to be here and here. So the hydronium ion concentration is going to be equal to 10 to the minus pH, which is just the rearranged form of our pH equation. So that's going to give us 2.4 times 10 to the minus 3 molar. And since that is much less than 10 to the minus 7, which is much greater than 10 to the minus 7, which is the hydronium ion concentration from water. So that's why we can assume that the effect of hydronium ions produced by the auto dissociation of water is going to be pretty irrelevant in this calculation. So that means that X is approximately equal to 2.4 times 10 to the minus 3 molar. So that's going to be approximately the hydronium ion concentration, which is going to be the same as approximately the phenyl acetate concentration. And why is that? Well, for every hydronium that's produced from phenylacetic acid, then there must also be a phenyl acetate anion created as well. So that means that our final equilibrium concentration of phenylacetic acid is going to be 0.12 minus X, which is approximately going to be equal to 0.12 molar. So we can then fill in these values. Since Ka is very small, that's why we're able to, or we're assuming that Ka is going to be very small, sorry. And so that's why we're assuming that the concentration of phenylacetic acid is going to be the same as the initial concentration. So Ka is equal to the hydronium ion concentration times the phenyl acetate concentration divided by the concentration of phenylacetic acid at equilibrium, but it's effectively the same as the concentration at the initial amount. So Ka is equal to 4.8 times 10 to the minus 5, which is a very small number. So we can then check our assumptions, because this is something that we need to always do to make sure that the assumptions that we made are reasonable. So checking the assumptions by finding the percent error in concentration. So hydronium ion concentration from water is equal to 1 times 10 to the minus 7 molar divided by the amount that we're saying has come from the dissociation. So, and then multiply that by 100 to get the percent. So that's equal to 4 times 10 to the minus 3. And so since that's less than 5%, we assume, or we have a justified assumption. Then we check to make sure that this idea that the equilibrium concentration of phenylacetic acid and phenylacetic acid at the initial are the same. So we check to see how much of our phenylacetic acid has actually dissociated. So that's just the concentration of the dissociated acid, which is the same as the hydronium ion concentration, divided by the initial concentration, which is 0.12 molar, times 100, and then that gives us the percentage of 2%. And so again, since that is less than 5%, we can say that our assumption is justified. So again, there's going to be a lot of examples going through this of these calculations. Most of them are fairly straightforward, but just make sure that you're familiar with how these all work. Try it out on your own, try to write it out, and then use these as a guide to learn. So propanoic acid, the formula is given there, will be simplified to HPR, is a carboxylic acid whose salts are used to slow mold growth in food. So it's kind of like a preservative. What is the hydronium ion concentration of 0.10 molar propanoic acid, where Ka is given as 1.3 times 10 to the minus 5. So again, as part of our solution, we make a few assumptions. We assume that we can use that the equilibrium and the initial concentrations of propanoic acid are the same. We can assume that the amount of hydronium ions produced by water is effectively negligible. And we also need to write out our balanced equation before we make our Ka. So Ka is going to be based on the balanced equation that we've created. So every or propanoic acid, it will dissociate whenever it is dissolved in water, which will give hydronium ions and propanoate ions. So Ka is equal to the concentration of hydronium times the concentration of propanoate over the concentration of propanoic acid, which is equal to 1.3 times 10 to the minus 5. And so that is given to us in this equation. So knowing this value, knowing the initial concentration of HPR, that means that we can actually solve this to find the hydronium ion concentration. So how can we do that? Well, since from our equation, we know that if one of these produces one of these and one of these, we can replace these with algebraic terms which are identical. So the concentration of H3O plus is going to be equal to the concentration of propanoate. So here we write out our reaction table again. We put the balanced equation at the top, and then we have our initial concentration. So we have water. It doesn't change because it's in massive amounts of excess since it's the solvent. We have 0.10 moles of, molar propanoic acid, and then we have no dissociated ions initially. Then during the change, what happens is we reduce the concentration of our propanoic acid, and we increase the concentration of our hydronium and our propanoate ions. And so at equilibrium, we have the sum of these two, initial and change, and that gives us our equilibrium concentrations. Now you can see that the terms here, the concentrations, can both be described as X, which means that we can substitute X into our Ka expression equation that we had on the previous slide. Our assumptions again are, since Ka is small, it's 1.3 times 10 to the minus 5. It's a very small number. We assume that the equilibrium lies heavily on the side of the starting materials. And so that means that X is going to be much less than 0.10. And so the concentration of propanoic acid at equilibrium is going to be effectively just the same as the initial 0.10 molar. So Ka is then equal to the concentration of hydronium times the concentration of propanoate divided by the concentration of the propanoic acid. And so that's equal to 1.3 times 10 to the minus 5, which is approximately going to be equal to x squared over 0.10, where x is coming from this table. It is replacing the hydronium ion concentration and the propanoate concentration. Since these are effectively equal to each other from our balanced equation and our reaction table, we can see that. So we rearrange the equation. So we multiply through by 0.10, and then we take the square root of everything to get the x value, which will be our hydronium ion concentration. And so that's equal to 1.1 times 10 to the minus 3 moles per liter. And so that's equal to the hydronium ion concentration. And so then we check our assumptions. We check that our dissociated fraction is below 5%. So the fraction of propanoic acid which has been dissociated is equal to 1.1 times 10 to the minus 3, which is the concentration of the hydronium ion and the concentrations of the propanoate anions. And so 1.1 times 10 to the minus 3 molar over 0.10 molar times 100% is equal to 1.1%. So this is less than 5%, and therefore our assumption is going to be justified. Concentration and extent of dissociation. So we've already encountered this a little bit already. So percent of the weak acid HA dissociated, well, it can also be for the strong acids, but usually you'll have 100% dissociation. So percent HA dissociated is equal to the concentration of the dissociated HA divided by the initial concentration of HA that was added to our solution times 100%. So as the initial concentration decreases, the percent dissociation of the acid will increase. And so HA plus water is in equilibrium with hydronium and our conjugate base, the A minus. So a decrease in the concentration, the initial concentration of HA means a decrease in the dissociated HA, which is equal to our hydronium concentration, which is equal to our conjugate base concentration, which causes a shift towards the products. And so the fraction of ions present increases even though the actual amount decreases. So what this means is that the more dilute a weak acid is, the more likely it is to dissociate. So the dissociated fraction of HA in a dilute solution is going to be higher than that in a more concentrated solution. And we'll see examples of that calculation as we go through. So we're going to look up now, we're going to compare two different solutions of HClO, hypochlorous acid. One is more concentrated than the other by about a factor of 10. So one order of magnitude different. We're going to see which one has the higher percent dissociation. Now, the relative amounts may be less for the less concentrated or the dilute solution, but we may see some interesting behavior in that the percent dissociation may be higher. So in 2011, researchers showed that hypochlorous acid, which is HClO, Ka equal to 2.9 times 10 to the minus 8, generated by white blood cells, kills bacteria. So this is one of the main vectors by which white blood cells can kill bacteria. So so we're just asked, we're not doing anything to do with the research. We're just asked to calculate the percent dissociation of these two. That was just a nice tidbit of information. So of course, we need to use the equation that we learned about on the previous slide, where percentage HClO dissociated is equal to the hypochlorous acid concentration of the dissociated part divided by the initial hypochlorous acid concentration times 100%. And we're asked to write the balanced equation to make a reaction table and to use the Ka expression where we assume limited dissociation as the Ka value is likely to be small. Oh, no, sorry, the Ka value is small. You can see here, 2.9 times 10 to the minus 8. It's a very weak acid. So as usual, we need to write our balanced equation, make our reaction table, and then make a Ka expression. So let's see how we do that. So here is our balanced equation. So hypochlorous acid dissolves in water to give our hydronium ions and our hypochlorate anions. So we write out our reaction table where we put in, this is for part A, we put in the initial concentration of hypochlorous acid, which is 0.40 molar. And then we also have our two concentrations of our hydronium and our hypochlorate. So the change here is minus x and plus x and plus x. And so the equilibrium here is 0.40 minus x, and then the other two are x and x. So since we assume that X is going to be much less than the initial concentration of our hypochlorous acid, then we assume that the equilibrium concentration of hypochlorous acid is the same as the initial, i.e. it is 0.40 molar. So Ka is then equal to H3O plus concentration times the concentration of our hypochlorite anions divided by our hypochlorous acid concentration, which is equal to 2.9 times 10 to the minus 8, which is equal to x squared over 0.4. So then we can obviously rearrange that to get our concentration of our hypochlorous acid, which is dissociated. So the amount of dissociated hypochlorous acid is going to be 1.1 times 10 to the minus 4 molar. So then we find out our percent dissociation, which is going to be 1.1 times 10 to the minus 4 molar divided by 0.40 molar times 100%, which is going to be equal to 0.028%. And so since that is less than 5%, our assumption is going to be justified. So what we're looking at here is in all cases really that the percentage dissociation should be less than 5% if we're going to be sort of allowed to accept that assumption. Usually the basis for the assumption is that Ka is small. And then if Ka is small, then we're able to use the equilibrium concentration of our weak acid as the initial concentration of our weak acid as the equilibrium concentration, in this case, both 0.40 molar. But we have to check that assumption at the end. And so we have to compare what we've calculated as the dissociated concentration with the initial or equilibrium concentration, and then find out what percentage the dissociated fraction makes up of the initial. And then if that is less than 5%, as it is here, then we can say that our assumption has been justified. So the next one then is to perform some calculations using, or perform the same calculation, using a different initial concentration of hypochlorous acid. In this case, we make use of a lower concentration by about an order of magnitude, which is 0.035 molar. So we have the same reaction table. We won't write it out here, but we can create the same expression for Ka. So Ka is equal to products over reactants, and that's equal to 2.9 times 10 to the minus 8. That 2.9 times 10 to the minus 8 was given to us in the question. Usually it's either given to us or it's the sort of the target of the question. And so that's going to be equal to x squared over 0.035 molar should be. All right, so we fixed that now. So it's now 0.035 as it should be. So that's our expression. Then we just rearrange and take the square root to find our x value, which is here. And then that's going to be equal to 3.2 times 10 to the minus 5 molar, which is going to be equal to the concentration of HClO dissociated. So then again, we put that into our equation where percent dissociation is equal to 3.2 times 10 to the minus 5 molar, and divide that by 0.035 molar, which is our initial concentration. We're assuming, since Ka is very small, that the initial and the final are going to be the same. And so we multiply that by 100%, and then we get 0.091%, which is actually higher than it was in the other one. Now, the total amount, here, the 3.2 times 10 to the minus 5 is smaller, but the percentage of dissociation is actually slightly higher. Okay, so equilibria of weak acids and bases. So weak acids and bases react only partially with water to form hydronium or hydroxide. And so pH calculations must be performed based on the Ka or Kb and the involved thermodynamic equilibrium. So Ha plus H2O gives an equilibrium with hydronium and the conjugate base, and Ka is the equilibrium constant for this. So with Ka, we can then form this relationship where Ka is equal to hydronium ion concentration times the conjugate base concentration over the Ha concentration. And then we can use this to solve for the hydronium ion concentration and then calculate pH. So an example of what is the pH of a 0.1 molar acetic acid solution where Ka is equal to 1.8 times 10 to the minus 5. We can make a number of assumptions about this. One, that since Ka is small, that our initial and equilibrium concentrations of acetic acid are pretty much going to be the same. And so we can form a special form of our Ka expression. So here we have our balanced equation on the left, where acetate plus water gives hydronium plus, or sorry, acetic acid plus water gives hydronium plus acetate. And so Ka then is equal to products over reactants, which is equal to X times X over C minus X, where X squared over C minus X is equal to Ka. So what is C? C is the initial concentration, in this case 1.0. And then X is obviously the one at the top here. So we have Ka, we have one unknown, which is X. We can form a quadratic expression for that, but we can simplify some. So since acetic acid is a weak acid, C is much higher than Ka. So the concentration, it's like what, 5 orders of magnitude higher. So C is much higher than Ka. And so simplifying C minus X to C is valid where C is much larger than K. And so X divided by C must be less than 0.05, which in this case, it most likely is. And so thus we can recreate our expression as Ka is equal to X squared over C. And so then X is going to be equal to the square root of C times Ka. Now, this might look a little bit sort of not exactly scary, but a little bit confusing, but actually it's exactly the same thing as we've been looking at before, where C is just the concentration, the initial concentration. Previously, we had hypochlorous acid that was 0.4 molar, and then we also had 0.035 molar for the less concentrated, the more dilute solution. So like we're just replacing that number with a letter C to make it more universal. And the justification is still the same. X over the initial concentration should still be less than 0.05 or less than 5%. So in this case, hydronium ion concentration is equal to the square root of C times Ka, since pH is equal to minus log the hydronium concentration. Then we can find the pH by substituting in our hydronium ion expression. So hydronium ion is equal to the square root of C times Ka. So we just substitute this into this equation, our pH equation. And so we get pH is equal to minus the log, the square root of C times Ka. And so pH of a weak acid solution is going to be based on the Ka and the initial concentration. And so for this acetic acid solution, because it is pretty concentrated at 1 molar, it is reasonably acidic. So it's going to be equal to minus the log to the base 10 of the square root of 1 times 1.8 times 10 to the minus 5. And so that will give us a concentration, or sorry, a pH of about 2.37. And so the fraction of ionized acetic acid is calculated to be this, where the fraction F is equal to the hydronium ion concentration divided by HA times 100%, which is equal to 0.0042 divided by 1 times 100%. So it's going to be equal to 0.42%. So pH calculations of diluted solutions. If water is added to further dilute acetic acid, the concentration of hydronium ions decreases. And so we're moving towards this value of the water auto dissociation hydronium ion concentration of 10 to the minus 7 molar. And so the fraction of the ionized acid acetate will increase. So an example of that is given here. So we have a very, very dilute acetic acid solution. So when we're asked, what is the pH of 0.0001 molar acetic acid, where Ka is the same, it is 1.8 times 10 to the minus 5. So our Ka expression is there. So it's going to be hydronium ion, it's going to be basically products over reactants. And so solving the above equation with the same approximation as before gives a 42% fraction of ionized acid. The approximation is not valid anymore, and the quadratic equation must be solved accurately. So here is the quadratic equation for that. It's actually based entirely on the same things. So it's Ka is equal to X squared over C minus X. So we just rearrange that to make it equal to 0. So it becomes just multiply through by C minus X and then rearrange it so that all of the terms are on one side. We make a quadratic equation where X squared plus KAX minus KAC is equal to 0, where this is X squared, this is MX, and this is C is equal to 0. And so we can rearrange that using quadratic equation, which is equal to minus Ka plus or minus the square root of Ka squared plus 4KAC divided by 2. And so obviously we can substitute that into our pH calculation. And so we can solve for basically anything using this. And so what we have, if we know our C value, which is our initial concentration, we know our Ka value, we can find the pH very easily. This is something very readily known in mathematics. So anyone studying mathematics is likely to know this already. So it's just a quadratic equation solver. So pH is equal to minus log of this expression, this function. And so we can determine the pH, and we can find that this very dilute solution has a much higher pH of 4.5. And so the fraction dissociated is actually also a lot higher. So it's 34% because the concentration of the hydronium ions is 3.4 times 10 to the minus 5 divided by 10 to the 4, which is our concentration of our acetic acid solution times 100% is going to be equal to 34%. Okay, so not all acids are the same. Some acids have more than one ionizable proton. These are called polyprotic acids. And in solution, each dissociation step has a different value for Ka. So usually what happens is that these are acids like phosphoric acid and sulfuric acid are probably the ones you would encounter the most often. Phosphoric acid is used in a multitude of applications in medical fields. It's also used in various industrial processes. Sulfuric acid, sometimes known as mineral acid, used a lot in industrial processes. So each step has a different Ka value. Usually the first proton to be removed is the easiest. So here we have phosphoric acid plus water. So phosphoric acid in water reacts to give the deprotonated conjugate base plus a hydronium ion. And we can see here Ka1 is for the products over reactants equal to 7.2 times 10 to the minus 3. Then we have here the next ionizable proton, which can be removed, which was the deprotonated conjugate base here. It is now the conjugate acid in this equation. So the conjugate acid forms the conjugate base, which is deprotonated plus a hydronium ion. And so this hydronium ion then has a much lower Ka value. So you can see here the Ka value, there's about a 5 order of magnitude difference here. So it's much easier to remove the first proton than it is to remove the second. And then the third becomes almost impossible to remove, where this will form the phosphate, and then this will kick out a hydronium, and we will end up with a Ka3, which is equal to 4.2 times 10 to the minus 13. And so there's a 10 order of magnitude difference between Ka1 and Ka3. And so the important thing here is not necessarily to remember these values, but just to understand that in polyprotic acids, they have more than one ionizable proton. There can be 3 and up to 3 in this case. Some others have 2, some others have different numbers. Usually it's 2 or 3. Then the first step is usually pretty easy, but the second and third steps get progressively more difficult. And so you can see that 5 orders of magnitude, then 10 orders of magnitude, it's just a lot less likely to happen. And so typically we usually neglect the hydronium ions produced after the first dissociation. So in most cases, in a more concentrated solution, the predominant species would be this one from only Ka. But if you had a very dilute solution, you're more likely to get the second and third steps. But generally speaking, we don't really include them because at this stage here, you're starting to get to producing fewer protons than water actually produces in its dissociation process. So it becomes a little bit complicated to determine whether it's really coming from water or it's really coming from your acid. So here are a few of these polyprotic acids. We have oxalic acid, an important acid in a lot of industrial processes. It's used as a sort of oxidizing agent. Sulfuric acid, phosphoric acid, arsenic acid. So sulfurous acid and phosphoric acid I've already talked about. We have arsenic acid, we have carbonic acid, and we have hydrosulfuric acid. So as we you can see here they're generally oxo acids. We talked about oxo acids before. Many of them are strong acids. Some are not so strong. We have the different Ka values here, going from low to high, where these are stronger acids than these down at the bottom. So our exercise now is to calculate equilibrium concentrations for a polyprotic acid. So calculating equilibrium concentrations for a polyprotic acid. So ascorbic acid, the formula is given there, is known as vitamin C, and it is a diprotic acid, meaning that it has two ionizable protons, and it is commonly found in citrus fruit. So we're being asked to calculate the concentration of all three forms, the undissociated form, the singly deprotonated, and the doubly deprotonated form. And they were asked to find the pH of 0.050 molar ascorbic acid. So our plan, as always, involves writing out our balanced equation, writing out our reaction table, and using our Ka expression. And then we're assuming that Ka2 contributes little, as it is very small, and we assume that ascorbic acid is a weak acid, which it most likely is because it's an organic acid. As well as that, we can assume that Ka2 contributes very little, because we've generally seen that whenever these Ka2 values are really small, they don't really do much. Now, what we can do is we can check that later on. Maybe we'll just do the calculation anyway and see, just to make sure. So write out our balanced equation here at the top. Balanced equation here at the top, and then we will write out our initial concentrations, which for our ascorbic acid is 0.050. And then we know that we don't have any dissociated species right at the start. Then we look at the change in concentration as we go through. We have our equilibrium concentrations here. And so then we fill in our Ka1 expression with the values that we have. So we have got the Ka value for Ka1 and Ka2 given to us in the question. So we get our points from the table. So it's going to be x squared over 0.05 minus x, which is the equilibrium concentrations of these species. Well, it's really x times x. That's why it's x squared. X is the singly deprotonated and hydronium ion concentration. So x times x gives us x squared. That's why it's x squared. So Ka1 is equal to x squared over 0.050 minus x. But since Ka is actually pretty small, times 10 to the minus 5, pretty small, then we make the assumption that the initial and equilibrium concentrations of ascorbic acid or weak acid are pretty much going to be the same. So then x is going to be equal to the concentration of hydronium ions, which is going to be equal to the concentration of the ascorbate anion, which is going to be equal to the square root of 0.050 times Ka, which is 1.0 times 10 to the minus 5. So that's that general equation that we learned earlier, where x is equal to the square root of C times Ka, where C is the concentration at equilibrium. And since usually these weak acids have the same equilibrium concentration, more or less, as the initial, C is usually obtainable very easily. So then 7.1 times 10 to the minus 4 molar is our hydronium ion, or our ascorbate ion concentration. And so pH is then equal to minus log concentration of H3O plus, which is equal to minus log 7.1 times 10 to the minus 4, which is equal to 3.15 as our pH for this solution. We have assumed, of course, that Ka2 is, the second deprotonation is effectively irrelevant. So we now need to check our two assumptions. The first was to assume that Ka2 contributes little, as it is very small. And so we see here that the hydronium ion concentration from the second deprotonation step is going to be equal to the square root of the first of H ascorbate times Ka2. So that's going to be 7.1 times 10 to the minus 4, which is what we calculated for the first step, times the Ka value, which is 6 times 10 to the minus 8 molar. This is less than the amount of hydronium ions produced by water, and so our assumption is justified. Then the second assumption is that ascorbic acid is a weak acid. And so this means this was the fact that we took our dissociated or equilibrium concentration of ascorbic acid as being the same as the initial concentration of ascorbic acid. And so the percent dissociation is equal to 7.1 times 10 to the minus 4 molar divided by 0.05 molar times 100%, gives us a value of 1.4% for our percent dissociated. So this is less than the 5% cutoff that we assume. And so that means that our assumption is going to be justified. So weak bases then, so a Bronsted-Lowry base is a species that accepts a proton. For a weak base that dissolves in water, B plus water gives us BH plus OH minus, and that is our equation for a weak base. Weak bases don't dissociate, they just obtain a proton from water and then produce the hydroxide. And so that's how bases increase the pH. So a base dissociation or base ionization constant is given by this, where Kb is equal to the concentration of BH plus times the concentration of OH minus divided by the concentration of the base. And note that no base actually dissociates in solution, but ions are produced when the base reacts with water. So yeah, the base isn't actually dissociating in any way. So how does this work? So let's look at the abstraction of a proton from water by the base methylamine. So methylamine is given here. So it's basically NH2 with a methane on it. So it's an ammonia with a methane in place of one of the hydrogens. And so the lone pair on nitrogen binds to the H plus. So here's the lone pair, it goes, gets this H plus, takes it from the water and forms the methylammonium ion and leaves us with a hydroxide. The hydroxide anion is, of course, the one which is going to increase our concentration of hydroxide ions in solution and therefore going to increase the pH. So here are a bunch of bases and sort of like their Kb values and then how that corresponds to an increase in their base strength. So the higher the Kb value they have, the better they are at getting the proton from water. So diethylamine here is at the top of this list of these bases. So it has 8.6 times 10 to the minus 4. Dimethylamine then is another base. It has a pretty high Kb value, albeit smaller. Methylamine, ammonia, pyridine, aniline. You'll see that if you know from organic chemistry, the more resonance stabilized the cation is going to be, the better it's going to be, or the higher the Kb value it's going to have. So you can see that these singly substituted has a better Kb value than the ammonia, and so on. So determining pH from Kb and initial B concentration. So dimethylamine, which we've already seen, is a key intermediate in detergent manufacture and has a Kb equal to 5.9 times 10 to the minus 4. We're asked, what is the pH of 1.5 molar dimethylamine? So of course, we have to write out our balanced equation. We have to know that dimethylamine reacts with water to produce dimethylammonium plus hydroxide. We write out our reaction table to take into consideration the concentration changes throughout the process of dissolution and reaching equilibrium. And then we need to write out our Kb expression. And we also have a number of assumptions that we need to make. So our assumptions are that we have a weak base, that Kb is going to be much larger than Kw, and therefore the hydroxide concentration that comes from water is going to be negligible. And then we're also assuming that Kb is small, so that means that the concentration of the dimethylamine is going to be at equilibrium is going to be effectively the same as the concentration initially. Remember that if we have just a concentration with square brackets and no subscript, so subscript here in it means initial, whereas here there is no subscript. So as we recall from the earlier slides of this session, this means that this is going to be an equilibrium concentration. So here is our balanced equation, and then the start of our reaction table. We've taken our balanced equation, which is dimethylamine plus water gives us dimethylammonium plus hydroxide. So then fill that into our table. We have our initial concentrations, which was 1.5 molar, which came from the the question. Then we have our other concentrations. Water is the solvent, so it's effectively unchanged. Then the other two are 0 initially. Then the change is minus X for the weak base, and then plus X for the dimethylammonium and the hydroxide ion concentrations. And at equilibrium, it's 1.5 minus X for the weak base. And then the other two products are going to be X and X. So again, since Kb is small, where X is going to be much less than 1.5. So that means we can assume that the initial and equilibrium concentrations of our weak base are going to be the same. And so 1.5 minus X becomes 1.5. So Kb is equal to the concentration of the products over reactants. And so that's going to be equal to 5.9 times 10 to the minus 4, which is approximately equal to X squared over 1.5. Remember that our X squared comes from the fact that for the product here, we have X times X. So X is equal to the hydroxide concentration, which is equal to 3.0 times 10 to the minus 2 molar. And so then we check our assumption to make sure that everything is justified. And 3.0 times 10 to the minus 2 molar is going to be divided by 1.5 molar, which is going to be multiplied by 100%, which is going to equal 2%. So therefore, this is less than 5%. And so our assumption can be said to be justified. Calculate the pH then. So remember that the pH is going to be equal to minus log concentration of the hydronium ions. And so we can recall that Kw is equal to the hydronium ion concentration times the hydroxide ion concentration, and is equal to 10 to the minus 14. And so the hydronium ion concentration is going to be equal to Kw over the hydroxide ion concentration, which is going to be equal to 1 times 10 to the minus 14, which is Kw, divided by the concentration of the hydroxide, which we just found out, which will give us a value of 3.3 times 10 to the minus 13 molar. So pH is going to be equal to minus log 3.3 times 10 to the minus 13, which is going to be equal to 12.48. So weak bases, the example here is the pH of 0.01 molar ammonia. So ammonia plus water gives ammonium plus hydroxide. Kb is equal to the ammonium concentration times the hydroxide concentration over ammonia. We have a similar expression here as we did for our Ka, if you recall, when we were creating the general expression. So in this case, we have X times X over C minus X, which is equal to X squared over C minus X. And so Kb is equal to 1.8 times 10 to the minus 5. And so our assumption also is that the concentration of the ammonium is equal to the concentration of the hydroxide. So we solve the above quadratic equation again for X. So Kb is equal to X squared over C minus X. So it's going to be equal to X squared over 0.01 minus X. So it's going to be equal to 1.8 times 10 to the minus 5, which is then going to give us a value of X is equal to 4.2 times 10 to the minus 4. So the hydronium ion concentration and pH of the solution is then obtained via Kw, where the hydronium ion concentration is equal to Kw divided by the hydroxide ion concentration, which is equal to 10 to the minus 14 divided by, which is Kw, divided by 4.2 times 10 to the minus 4, which is the concentration of our hydroxide species, which we got up here from our quadratic equation. And then that's going to give us a pH value, which is equal to minus log of this term here, which is the hydronium ion concentration, which will give us a pH value of 10.6, which is in the basic range, which we would expect since ammonia is a weak base. And it's not particularly strong whenever this scale goes up to values in excess of 14. So how did we solve this? Well, we just used the solver equation that we had before, Ka. It's exactly the same. It's just we substitute Ka for Kb. So anions of weak acids as weak bases. So we recall that one of the problems that weak acids and bases have is that, especially with weak acids, is that whenever they produce their conjugate base, the A minus is actually a pretty good base. And so what it does is it reacts with more water to form the acid again, HA, and to form a hydroxide ion, which will consume any of the hydronium ions that have been produced by the acid dissociating in the first place. So that Ka, or that A minus abstracting a proton, obviously has a Kb value. I mean, it's working as a base, so there must be a Kb value associated with that. So this Kb then is equal to the products of reactants, where the Kb is equal to Kc times the concentration of water, which is usually just taken as 1. So a solution of HA is acidic, while a solution of A minus is going to be basic. So HF is a weak acid plus water gives H3O plus F minus, the fluoride. So HF is a weak acid, much weaker than hydronium, so the equilibrium lies to the left. Remember that generally the equilibrium will lie on the side which produces the weaker acid or base. In this case, HF is a weaker acid than hydronium, so it wants to stay on the left-hand side. The concentration of HF is much larger than fluoride, but the concentration of hydronium from HF is going to be greater than the hydroxide produced from water. And so that means overall the solution will be acidic. And so it's this process at the bottom, which is what ensures that weak acids are actually acidic. Even though there's this competing base reaction, because of the fact that the amount of hydronium ions produced is from the weak acid is still greater than the amount of hydroxide produced from water, basically means that the solution is still going to be generally acidic. So if sodium fluoride is then dissolved in water, we don't have the hydronium anymore. And so that means that F minus will act as a weak base. Sodium ions do not really act that well as, are just spectators really. So equilibrium obviously favors the formation of the weaker acid and base. And so that means that although HF is a weak acid, it is stronger acid than water. And so this equilibrium will lie to the left. And so the fluoride concentration is going to be less than the concentration of HF, but the hydroxide ion concentration is going to be greater than H3O plus. And so the solution, therefore, is going to be basic. So Ka and Kb for conjugate acid-base pairs. So for this, we have a weak acid HA plus water giving hydronium ion, giving a hydronium ion or a proton H plus or H3O plus A minus, which is the conjugate base of HA. And so then we can have obviously the competing reaction where A minus plus water gives us HA plus the hydroxide. And so we can cancel out some of the terms on both sides. And what we end up with is, in fact, the auto dissociation of water. So Kc for the overall reaction then is going to be K1 times K2. So we learned about that back in equilibrium lecture. And so the hydronium ion concentration times the conjugate base concentration over HA times HA times OH minus over A minus basically gives us the hydronium ion concentration times the hydroxide ion concentration, because A minus cancels with A minus, HA cancels with HA, and so we're left with just H3O plus concentration times OH minus concentration. And so this is Ka times Kb is equal to Kw, which we already found out. And so this relationship is true for any conjugate acid-base pair. So determining the pH of a solution of A minus, so sodium acetate is given there. And so this has applications in photographic development and textile dyeing. What is the pH of 0.25 molar sodium acetate at 25 degrees Celsius when Ka of acetic acid is 1.8 times 10 to the minus 5? Remember that any conjugate acid-base pair, Ka times Kb is equal to Kw. We just saw that on the previous slide. So our plan here is going to be understand that sodium salts are water soluble, that acetate is the conjugate base of acetic acid. We're going to write a base dissociation equation. We're going to determine Kb. We're going to prepare a reaction table, and we're going to assume that sodium acetate completely dissociates in water, which seems reasonable since the sodium ions are water soluble, or sodium salts are generally water soluble. So here's our balanced equation. So we have acetate plus water gives acetic acid plus OH minus. And so the Kb for that reaction is going to be products of reactants. So it's going to be acetic acid times the concentration of hydroxide divided by the acetate anion concentration. And so then the concentration here is equal to, we put our balanced equation on top. So we get our initial concentration. So from our question, we had 0.25 moles or molar a solution of sodium acetate. Then our concentrations of our acetic acid and our hydroxide are 0 and 0 respectively. The changes then are minus X and plus X's respectively. So these are all just reaction tables that we've seen before several times already today. And so the equilibrium concentrations then are going to be 0.25 minus X. And so we're going to have X and X on here. Then Kb is going to be equal to Kw over Ka, which is going to be equal to 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. And so that's going to be equal to 5.6 times 10 to the minus 10 for the Kb of acetate. Okay. So now that we have the Kb value, we can continue to work on the rest of the problem. So since Kb is equal to 5.6 times 10 to the minus 10, that's going to be then equal to this, which is our base dissociation expression, where we have the concentration of acetic acid times the concentration of hydroxide all over the acetate concentration. So that's going to be approximately equal to X squared over 0.25, 0.25 being the initial concentration of the sodium acetate, but it's also going to be probably our equilibrium concentration because we're assuming that it's going to be the amount here that's actually going to form the acetic acid is going to be very small and minimal. So X is then going to be equal to the hydroxide concentration, which is going to be equal to 1.2 times 10 to the minus 5 molar. And so we're checking the assumptions here. 1.25 times 10 to the minus 5 divided by 0.25 times 100% is going to be equal to 4.8 times 10 to the minus 3%, which is much less than our 5% cutoff. And so that's going to mean that our assumption is in fact justified. Then we can use this to find our hydronium ion concentration. So our hydronium ion concentration is going to be equal to Kw over the hydroxide concentration. Remember that Kw is equal to hydronium ion concentration times hydroxide ion concentration, which is equal to 1.0 times 10 to the minus 14. So fill in the values here. So Kw is this value. Our hydroxide ion concentration has this value, which we got from here. Remember that it's acetate times hydroxide, or acetic acid times hydroxide. So if acetic acid concentration is this, then hydroxide ion concentration also needs to be this. So they're there. So that means our hydronium ion concentration is really small, much less than the amount that's produced by water. So the pH here is going to be equal, it's going to be basic, basically. It's going to be equal to minus log the concentration of hydronium ion concentration. So it's going to be minus log 8.3 times 10 to the minus 10, which is going to be equal to 9.08. That's going to be basic, which shows us that a solution of sodium acetate will produce a basic solution. Acid strength of non-metal hydrides. So we're looking at non-metal hydrides. So like not things like sodium hydride, but other materials. So for non-metal hydrides, acid strength depends on electronegativity of the central non-metal E and the strength of the EH bond. So this is in non-metal hydrides. So across a period, acid strength increases and electronegativity increases across a period. So the acidity of EH increases, and down a group, acid strength also increases. So the length of the EH bond increases down a group, and its bond strength therefore decreases. So like non-metal hydrides, things like HF, HCl, HBr, things like that. Those are all non-metal hydrides. So here we have non-metal hydrides of group 6A and group 7A. And so the effective atomic and molecular properties on non-metal hydride acidity. So here we have electronegativity increases, so acidity increases. So we have more electronegative atoms here than here. So this is going to be more acidic than water, for example. Then bond strength decreases as we go down. So we're going to see these are the least acidic, these are the most acidic. So we have HI being the most acidic. Tellurium dihydride going to be more acidic than selenium dihydride, which is going to be less acidic than, for example, hydrobromic acid. Acid strength of oxo acids then. So oxo acids we talked about before. So oxo acids are strong acids if the difference between the number of oxygens and the number of hydrogens is 2 or more, and they're weak acids if it's going to be less. So here we have on the right-hand side here, this is sulfuric acid. So we can see 1, 2, 3, 4 red oxygen atoms and 2 white hydrogen atoms surrounding a central sulfur, yellow. So there are 4 oxygens and there are 2 hydrogens. So that means there's a difference of 2. So this is a strong oxo acid. Then we can also have other oxo acids such as HOCl, which is the hypochlorous acid. There is a difference of 0 between the number of hydrogens and oxygens, and that indicates to us that this is a weak acid. So all oxo acids have acidic H bonded to an oxygen atom. And so acid strength of oxo acids depends on the electronegativity of the central nonmetal E and the number of oxygen atoms around E. In this case, E is sulfur, and in this case, E is going to be chlorine. And so for oxo acids with the same number of oxygen atoms, acid strength increases as the electronegativity of E increases. So for oxo acids with different numbers of oxygen atoms, acid strength increases with the number of oxygen atoms. So here we see the relative strength of oxo acids. So as we increase electronegativity, so too does acidity increase. So you can see there here that the hypochlorous acid is going to be more acidic than hypobromic bromus and more acidic than hyperiodus. And then here, as the number of oxygen atoms increases, so acidity increases, these green arrows indicate the direction of the electron pull away from the hydrogen. So this area is highly electronegative. And so that means that it's really, really, really easy to remove this proton, which means that we end up with a more acidic oxo acid with more oxygen atoms. Hydrated metal ions. So some hydrated metal ions are able to transfer H plus to water. So these metal ions will form acidic solutions because by transferring H plus to water, we produce the hydronium ion, and the hydronium ion increases in concentration will form acidic solutions. So if we consider a metal ion in solution as Mn plus, where M represents some metal and N is the number of electrons that are deficient, then Mn plus dissolved in water plus water will give us this hydrated metal where there are a number of waters attached. So if Mn plus is small and highly charged, it will withdraw enough electron density from the OH bonds of the bound water molecules to release H plus. And so here we have the hydrated metal ion, and then it reacts with more water to form this hydrated metal ion with hydroxides now, which reduces the charge because the hydroxide is negatively charged, plus hydronium ions. So this is the process by which these hydrated metal ions produce hydronium, which is going to be fundamental in producing our acidic solution. And so acidic behavior of the hydrated aluminium 3 plus ion. So electron density is drawn towards the aluminium 3 plus. And because this electron density is drawn towards the aluminium 3 plus, this bond becomes more polar, which weakens this oxygen hydrogen bond, which makes it easier for the water to act as a base and come in and take this hydrogen. So that means that we end up with this water molecule becoming a hydroxide. And then because it's bound to the aluminium, it's acting as what's called a ligand. So it doesn't actually change the pH of the solution. but the hydronium ion is now present in solution and it's free to act and to change the pH, in which case it will increase the concentration of hydronium ions, and this will cause a decrease in the pH as the solution becomes more acidic. Let's check comprehension. So we're asked, what is the percent dissociation of 0.35 molar hypochlorous acid aqueous solution? And so our Ka is 2.9 times 10 to the minus 8 given here. Again, as usual, pause for more time, try to do it yourself. We'll go through the answer, but really the point of this is for you to try yourself and see if you can get the answer that we get in this slide. So pause for more time if you need it. Okay, we're about to go through the answer. Please pause if you need more time. Okay, answer coming now. All right, so as usual, we need to create a balanced equation. So our hypochlorous acid reacts with water to give hydronium ions plus the hypochlorate. We have initial concentrations of 0.35 molar. We assume it's a weak acid. The Ka is very small, so it's probably true. The change here is minus x and plus x plus x. So the equilibrium then is 0.35 minus x. The concentration of H3O plus and hypochlorate is x and x. So since Ka is small, we assume that the x value is going to be much less than 0.35 molar. And so therefore the equilibrium concentration of the HClO is going to be approximately 0.35 molar. Then the Ka is formed as products over reactants, which is going to be equal to 2.9 times 10 to the minus 8. So that's going to be equal to x squared over 0.35, which is our equilibrium concentration of our hypochlorous acid, which is assumed to be basically the same as the initial because of the very low dissociation constant. X can then be found as so, which gives us a value of 1.0 times 10 to the 4 molar, which is going to be the same as the concentration of dissociated hypochlorous acid. And so the percent dissociation is going to be equal to 1.0 times 10 to the minus 4 molar over 0.35 molar times 100%. Gives us 0.029% dissociated, very, very small. And so that's less than our 5%. So therefore, our assumption is going to be justified.